Hello everyone. Today we are going to study stimulated Raman scattering and stimulated Brillouin scattering. Following are the contents that we are going to cover today. Introduction, SRS, SBS and their references. So the origin of SRS and SBS lies in ultra-fast third order susceptibility Chi3. Chi3 is a complex quantity. It has both real as well as imaginary part in it. The imaginary part of Chi3 leads to stimulated Brillouin scattering SBS and stimulated Raman scattering SRS. These nonlinearities are due to inelastic scattering process. Stimulated Raman scattering SRS. SRS is interaction between light wave, that is incident light, and the vibrational modes of silica molecules, that is the material. If a photon with energy h nu1 is incident on a molecule having vibrational frequency nu m, the molecule can absorb some energy from the photon. So some energy from the incident photon is absorbed by the material. In this interaction, the photon is scattered, thereby attaining a lower frequency nu2, which is obviously having longer wavelength because wavelength and frequency are inversely proportional to each other. And this scattered light will have lower energy h nu2. The modified photon is called Stokes photon, which is at longer wavelength and lower energy. Because the optical signal wave that is injected into a fiber is source of the interacting photons. It is called the pump wave because it supplies power for the generated wave. This process generates scattered light at a wavelength longer than that of the incident light that we have already discussed. If another signal is already present at this longer wavelength lambda2, then that signal is amplified because already that signal lambda2 would be having some power. And because of this Stokes photon, we have got one more signal that is present at lambda2. So power corresponding to these two signals will add up. So its signal corresponding to lambda2 would be amplified. The power transferred to a higher wavelength channel increases approximately linearly with channel spacing up to 16 terahertz or 125 nanometer at 1550 nanometer band. And then it drops off sharply for the larger spacing. We will see it with the help of a graph in the next slide. So this is how stimulated Raman scattering works. Suppose we have a WDM system where we have four wavelengths, lambda 1, lambda 2, lambda 3 and lambda 4. When these four wavelengths will get transmitted through this optical fiber, SRS effect will take place. We have chosen these four wavelengths such that lambda 4 is the longest wavelength, lambda 3 is shorter, lambda 2 is even shorter, and lambda 1 is the shortest wavelength. So when these four wavelengths will affect SRS inside this optical fiber, at the output we will get a signal like this, where some power from lambda 1 will get transferred to signal corresponding to lambda 2. So lambda 2 has got amplified and lambda 1 has depleted. In a similar fashion, some power from lambda 2 will get transferred to the signal corresponding to lambda 3, and some power from signal corresponding to lambda 3 will get transferred to the signal corresponding to lambda 4. So we can see that this power transfer takes place in a linear fashion almost. From the lower graph, what we can see is on the x-axis we have taken the channel separation, and on the y-axis we have taken the Raman gain coefficient. So you can see that for the channel spacing delta lambda up to 125 nanometer, this spacing is 125 nanometer up to this. So up to 125 nanometer channel spacing, this gain is almost linear. It's not exactly linear, but it can be approximated by a linear graph. So it is almost linear up to 125 nanometers of channel spacing. After 125 nanometer, this gain drops off very sharply. So this is what we were trying to understand, that if this channel spacing between lambda 1 and lambda 2, lambda 2 and lambda 3, lambda 3 and lambda 4 is up to 125 nanometer, then this linear power transfer will take place. Next is stimulated Brillouin scattering or SBS. In stimulated Brillouin scattering, a strong optical signal generates an acoustic wave that produces vibration in the refractive index. So SBS is mainly due to variation in the refractive index. The index variations The index variations causes light waves to scatter in the backward direction. Here the light wave will travel in the backward direction towards the transmitter. This backscattered light experiences gain from the forward propagating signals, which leads to depletion of the signal power. The frequency of scattered light experiences a Doppler shift, which is given by nu b equal to twice n Vs by lambda, where n is refractive index and Vs is velocity of the sound in the fiber material. So below a signal level called the SPS threshold, the transmitted power increases linearly with input level, and SPS is very negligible below a threshold value. Beyond the SPS threshold, percentage increase in signal depletion grows with signal strength. So as we increase the input signal power, as beyond the SPS threshold, the percentage decrease in the signal will grow. Beyond the SPS limit, any additional launched optical power is scattered backward in the fiber. And SPS affects the power in same channel only. Power transfer doesn't take place from one channel to another channel in case of a WDM system like SRS. We can understand this phenomena by these graphs. In the first graph, on the x-axis we have taken fiber injected power, on the y-axis we have taken carrier to noise ratio. So here what we can understand is, as we are increasing the input power on the x-axis, we can see that carrier to noise ratio is increasing linearly. And backscattered power is also increasing slowly. But as soon as the input power crosses certain threshold value, this backscattered power increases very sharply. And because of the sharp increase in the backward scattering power, our CNR starts reducing. We can also understand it with the help of this second graph, where on the x-axis we have taken the relative transmitted optical power. On the y-axis we have plotted two things: signal power and backscattering power. So as we increase the input signal power on the x-axis, what we can see is that the output signal power increases in a linear fashion, which should be ideally the case. And backscattered power is also increasing slowly. But as soon as your input power crosses this threshold for the SPS threshold, this backscattered power increases very rapidly. And because of the sharp increase in the SBS or backscattered power, your signal power now do not increase linearly. Rather, it reduces or it depletes. And this is mainly because of backscattering power or SBS effect. So this was SRS and SPS for you. In the next lecture, we will study cell phase modulation and cross phase modulation. If you have any queries, you can post them at discussion forum of www.chetanselwal.com. For the lecture notes also, you can visit this website. Thank you.